Section 16.7 deals with surface integrals. We are going to do our best today to try to draw the relationship between surface integrals and surface area with that relationship that we saw between line integrals and arc length. So if you recall from previous sections, we have our line integrals of some scalar function f with respect to arc length along some curve. How we actually evaluated them is that we parameterized our curve. I guess we didn't really necessarily, we did kind of use r, whatever, but we parameterized our x, we parameterized our y, and then our ds got replaced with the square root of x prime squared plus y prime squared dt. We kind of thought about that kind of like r of t dotted with, or not necessarily dotted with, but magnitude of r prime of t. So what we're going to be kind of looking at today is going to try to find a similar relationship set of in these dimensions for line integrals and arc length to surface integrals and surface area. So we are going to define our surface integral of f over our surface s in such a way that when our function is equal to 1, that would give us our surface area, just like when our f for our line integral was equal to 1, that simply gave us our arc length. Should make sense because we're just dealing with that guy right there. So we're going to start with parametric surfaces. I don't know if we'll get to special cases today. So suppose we have a surface S that has a vector equation r of uv, 3 functions, some x, y, and z of uv. Just like we were talking about with surface area, we kind of imagine our UV space in the domain for which we're taking something that corresponds to a patch on a surface. If we get the areas of these patches, can form this Riemann sum down here. This all kind of should look familiar by this point. Basically, where we're going to get our surface integral from are these Riemann sums. That is going to be our notation right there. Please note that it is similar to our scalar line integral. Quite similar. So we're, instead of using ds with the little s, we're using the big S. And then we're doing a double integral. Oops, if I'm writing this the way to match this, we're going from a single integral to a double integral. So what are we going to be approximating our delta S sub I j with, for similar reasons as we talked about in our previous section? That is going to be our r sub u cross r sub v. The magnitude of that cross product, delta u delta v, and our limits would of course take that to get to our integral, which we're going to see below. I will remind you that r sub u, our tangent vector, is partial of x with respect to u, partial of y with respect to u, partial z with respect to u, and then r sub v is our partial of x with respect to v, partial of y with respect to v, and partial of z with respect to v. So, in a very similar fashion as to how we evaluated line integrals, we're going to evaluate surface integrals the same way. We are going to parameterize the surface, and then we figure out how to represent our change in surface area right there. In this case, we're going to be using the approximations of our areas of our little parallelograms with our magnitude of our cross products. of those two tangent vectors in the u and v directions. So this right here, this is an important thing. This is your surface integral of f over s. You'll notice we are replacing this ds with, instead of like r prime dt, or excuse me, magnitude of r prime dt, now it is the magnitude of r sub u cross r sub v. Similar idea, I think you might notice. So, oh, I actually have it written down here. I forgot about that. You'll notice that we replaced this ds with like the magnitude of a derivative thing. Magnitude of a derivative thing dt. Kind of have the same idea here, magnitude of a derivative thing, but we have two different directions in which we have to take our derivatives. So we do a cross product to put those together. So here is, folks, our first example. Compute the surface integral. You'll notice the big S right here. That'll give you the idea that it's a surface integral. You'll also notice that it's a double integral and not a single integral. So we're going to compute the surface integral, double integral, or surface integral of x squared ds over s, where s is the unit sphere, x squared plus y squared plus z squared equals 1. The easiest way for us to parameterize this surface, because we can't solve for one of the variables that would introduce two functions, a plus and a minus of a square root. If it is a sphere, why don't we just use spherical coordinates? I will be honest, coming up with the cross product of the partial derivatives is going to take a little bit, to the point where you might want to end up memorizing this one, but we're going to do it one time fully through here together. So our parametric representation, because our sphere has a radius of 1, let's just use phi and theta instead of u and v. We can do 1 sine phi cosine theta, 1 sine phi sine theta, and 1 cosine phi. The restrictions on our parameters, if you remember, for phi we only go to pi, and then for theta we go to 2 pi. So if we're going to evaluate this surface integral, we know what we're already plugging in for x squared, but the real work is going to come into representing our ds through our parameters. So let's start with partial derivative of r with respect to phi. So here we go, folks. That is going to be cosine phi cosine theta, cosine phi sine theta, and then negative sine phi. Our partial derivative with respect to theta is going to be negative sine phi sine theta. Don't get confused and try to make that like a sine squared. We got sine phi cosine theta. And then we have, oh nice, 0. So now we need the cross product. Write this guy out, give myself enough space here, so I'm going to go down the columns instead of across the rows. We have cosine phi cosine theta, and then we have negative sine phi sine theta. J cosine phi sine theta, and sine phi cosine theta. And then we have k negative sine phi and 0. So taking our cross product, our first component is going to be 0 minus negative. So that'll be positive sine squared phi cosine theta. Our second component, again, I'm going to do the diagonals backwards so I don't have to do a negative quantity. So that is going to be 0 minus negative times negative, so it's still negative. Sine squared, sorry about that, sine squared phi sine theta. I'm sorry, I'm doing that backwards. That's got to be positive. We're doing this diagonal first. So it is positive minus 0. My bad. And then moving on to our last one, we got a bunch of stuff that we have going on here. So we have cosine phi, cosine squared theta. Cosine phi, sine phi, cosine squared theta, minus negatives, that's going to be plus cosine phi, sine squared. Cosine phi, sine squared theta. And you'll notice with the two things in front of the cosine squared and sine squareds of theta, that is actually going to simplify to sine squared phi cosine theta, sine squared phi sine theta, and then cosine phi sine phi. And then, of course, we have to take the magnitude of this, which should be the square root of all of those components squared. So let's write them down, added together. Sine to the fourth phi cosine squared theta plus sine to the fourth phi sine squared theta. You might notice there we might be able to do something with those two, plus cosine squared phi sine squared phi. When we look at these two, they add together to make sine to the fourth phi. And we have a cosine squared phi sine squared phi. And you might not notice this immediately, but if I write this way, if I write instead of sine to the fourth, if I instead write it as sine squared phi sine squared phi plus cosine squared phi sine squared phi, you'll notice that because of those two things, this actually ends up being the square root of sine squared of phi. Be careful not to just say that this is sine phi without giving this a moment's thought. The way our domain is, this has to be positive because phi is between 0 and pi and sine is positive between 0 and pi. But in general, this would have to be the absolute value of sine of phi. Don't forget that. You do have to check signs with that kind of stuff with square roots. So now that we finally got this cross product, we can take our surface integral over s of x squared ds and rewrite this as the double integral over our parametric region D. What is x? X is, we got to go all the way back up to the top. X is sine phi cosine theta. So sine phi cosine theta quantity squared. And our ds is going to be sine of phi dA. And now we have to look at our region for our parameters. That's just a rectangular region. So this is going to become integral from 0 to, it doesn't really matter which one you do first, 0 to 2 pi, 0 to pi of sine cubed of phi cosine squared theta d phi d theta. Because of the rectangular region, we can split this up into two integrals. So integral 0 to 2 pi of cosine squared theta d theta times integral 0 to pi of sine cubed of phi d phi. With the cosine squared, remember we have to use our power reduction formula, so we would be integrating, excuse me, 1 plus cosine 2 theta over 2 d theta. And then for an odd power of sine or cosine, we actually break that up into an even power and one left over. So we actually think about that one as sine squared of phi times sine of phi d phi, because that allows us to take that one, which I'll do the work over here, is the integral from 0 to pi of 1 minus cosine squared of phi times sine of phi d phi, and then we get to do substitution there. So I'll do the first one in red. That is going to be theta over 2 plus sine of 2 theta over 4. And that's going to be evaluated from 2 pi and at 0. and we're going to multiply that to here. I haven't used u, I guess I can use u sub here. U would be your 1 minus cosine squared. I'm sorry, no, that's not right. I'm sorry, I'm underthinking that. U is actually equal to cosine, so du equals negative sine theta d theta. So we can replace this with negative du, and then we have our integral 1 minus u squared, and we just have to do the opposite right there. So that actually ends up giving us, I'll write it down here. We integrate 1, I guess I'll just do the u squared. We get 1/3 u cubed, which is cosine, so we have cosine cubed of phi over 3. Then we have this minus 1 because of this negative right here. Integral of that is going to be minus u, so it's going to be minus cosine phi. And we're going to be evaluating that at pi and 0. So when we get through with all of this junk right here, what do we end up with? That is going to be pi plus 0 minus 0 plus 0 times cosine of pi is negative 1 to the third is negative 1, so that's negative 1/3 minus negative 1, so that's plus 1, minus cosine of 0 is 1, so that's going to be 1/3 minus 1. So this gives us pi times, this is 2/3, this is 2/3, and we'd add them, I guess, because that'd be negative 2/3, so that'd be 4/3, so pi times 4/3, so our answer is 4 pi over 3. I think the last example we'll do today, actually, nope, I want to do the takeaways in the next one. So we'll do one more example for today, and then we'll pick up the rest on Monday. Just like we had our center of mass application from line integrals, where if we wanted the mass, we could do the line integral along C of rho ds. We have the same thing, same type of application for surface integrals. So if a thin sheet, say of aluminum foil, has the shape of a surface S and the density, mass per unit area, at a point xyz is given by some function rho, then the total mass of the sheet can be calculated using this double integral. So now, again, it's a surface and not along a curve. So when we were talking about the ones with line integrals, we were talking a lot about like wires, for instance. Whereas this, we're talking about surface, like a sheet of aluminum foil. Center of mass, unsurprisingly, x bar, y bar, and z bar is 1 over the mass times that variable times the rho function. And we do those surface integrals. So last thing for today is going to be this example, example number 2. Consider the two-dimensional sheet given by S right here. Y is defined as 2x squared plus 1, where x is between 0 and 2, and z is between 4 and 8. This is a surface in 3 space. So it gives us where our density of the sheet in kilograms per meter squared is rho equals xz squared. Find the mass of the sheet. So, folks, we need to find a parametric representation of our surface. So this is the surface. Don't confuse that with the density function rho. So if we have y equal something in terms of x, it might make sense for our parameterization to maybe be, let's call x u. So then we can call y 2u squared plus 1, getting that from right there. And then z is not defined through x or y things, so that gets to be on its own, so maybe we just call that 1v. Where u is bounded between 0 and 2, and v is bounded between 4 and 8. Just like before, if we're going to take this surface integral, we need to find our partials. So let's do derivative with respect to u, which would be 1 for u and 0. And then our partial with respect to v, which would be 0, 0, 1. That's pretty easy. Taking the cross product right here, I'm going to try to do this one without writing down the determinant. I believe that's going to give us 4u, and then we need to do 0 minus 1, so that would be -1, if I am not mistaken. And then finally, with our last one, 0 minus 0, so we get 0. We will need the magnitude of our cross product, which is going to be the square root of 16u squared plus 1. So we can calculate our mass by doing the surface integral over our surface S of rho ds, which we can turn into our double integral over our parametric region D. It's right there, folks. And then what is our rho? That is xz squared. So if we're plugging in something for x, our parameterization for x is u. And z squared, that would be v squared. So that'd be uv squared. And then our ds gets replaced by the magnitude of the cross product, square root of 16u squared plus 1. Du dv, I'll write, actually let's make the decision. Which one are we going to want to do first? I think we probably want to get through the u stuff. It doesn't actually matter. I'll just do du dv, whatever, don't care. So we can write our bounds then. So that would be integral 4 to 8, integral 0 to 2 of uv squared square root of 16u squared plus 1 du dv. We need some substitution here to do this integral with respect to u first. So if we call, like for instance, alpha equals 16u squared plus 1, then d alpha equals 32u du, and we have the u du that we're working with, so we just need to incorporate a substitution factor of 1/32. So that is going to be the integral from 4 to 8 of 1 over 32. We're integrating this thing to the 1/2, so that is going to give me v squared times 2/3, 16u squared plus 1 to the 3/2, where we will be plugging in u equals 2 and u equals 0. All right, let's see. What does that give us when we plug in 2 for u? Let's see. We can just take out the 1/48. That might make our lives easy if we bring those out to the front. Integral 4 to 8 of v squared times, if we plug in 2 for u, that is 16 times 4. 64 plus 1 is 65. So 65 to the 3/2, aka 65 root 65. When we plug in 0, it's not 0, it's 1, so don't forget that we have to subtract 1 right there. So it's this integral dv now. When we integrate with respect to v, we're just going to get 65 root 65 minus 1 over 48 times v cubed over 3, and we're evaluating that at 8 and at 4. I'm going to be a little lazy here. I'm not going to do 8 to the 3rd and figure out how that works with everything. I think I'm just going to give you the answer is 28/9 times 65 root 65 minus 1. All right, thank you for watching this or filling this out. On Monday, we'll continue with our surface integrals. We'll talk a little bit more about our surface integrals with our scalar functions. Got a couple examples before we get to the day 3 and 4 notes when we're doing surface integrals with vector fields. Have a nice weekend, everybody.